Welcome. So we have been discussing about discrimination-based approaches to understand neuronal encoding and decoding. We introduced you to the idea of this approach, and we saw that using D prime, which was used for based on ideal observer analysis, how to discriminate, how to use it to measure discriminability based on rates of responses. Since since D prime suffers from the fact that there is an assumption about the distribution, um, we introduced that we can use the Kullback Leibler distance, which is an information theoretic measure of distance between distributions that can be used to quantify discriminability as another way to look at the ideal observer based approach. Uh, so if we remind ourselves what KL distance is, so let us say P is one distribution of a particular on a particular space, Q is another distribution on the same space. Let us say X is the random variable and it takes on values over many possible values little x, and our KL distance, which is dKL, which we write it as PQ, is equal to summation x, all possible values taken, Px log of Px by Qx. And so here when we think about it, so we are not making any assumptions about the distribution. So let us say our x-axis is this, even if our random variable is say rate, let us say we first think of it as a discrete variable, where let us say we have the possible rates that range between R1 to R2, and P of x is empirically determined based on our observations. That is, if this is the probability of observing rate equal to a particular R, or x equal to a particular little x equal to a particular little x, then we can create a histogram based on, so this is for stimulus 1 and another histogram based on responses to stimulus 2. These are our different rates, and that is the probability of observing the different rates x, and similarly we have a histogram that would be looking like this and very low values on the outsides. So we simply use this px's. So these are the different px's, px1, px2, and so on up to here px, let us say capital N. Let us say there are capital N possible rates that we have, and so this one is P, this one is Q, and we simply use this measure of KL distance by summing over all the different bins. We get a distance between the two distributions, and as the distance increases, the more is the discriminability between two stimuli. And as we have said that these methods suffer from measures of from bias and I mean essentially a large amount of data requirement. So we will not go into the discussions of how to tackle these problems. Instead, we will refer you to possible methods in the reading material. However, remember that those are important whenever we do such calculations. So now let us go back and see what the KL distance for our continuous case is going to be if our distributions are indeed Gaussian with two different means and equal standard deviations. So let us say that is we have DKL of P and Q. Now P is 1 by square root 2 pi sigma squared exp minus x minus mu 1 squared by 2 sigma squared. So we have a continuous distribution, and Q is basically the same thing, only our mu 1 is replaced by mu 2. So these are the two distributions that are being discriminated. So what is the KL distance then from between these two? So we simply apply, instead of the sum we will have the integral over, in this case, minus infinity to infinity. This is a problem in the sense that already says that it is not possible for the rate distribution to be Gaussian at all. That already is wrong, because rates cannot be negative. However, we can say that it is negligible below 0. The mass or the density or the total mass below 0 is negligible, and then we are okay. So we continue on with the KL distance, that is, now we are writing this Px and log of Px by Qx. So Px by Qx, we cancel the square root 2 pi sigma squared, and we are left with exp minus x minus mu 1 squared divided by 2 sigma squared divided by exp minus x minus mu 2 squared divided by 2 sigma squared, and we have dx. Now remember, Px is that same Gaussian, okay, that is normal 0 sigma squared. Now if we look at this term, so it is simply the difference of what we have in the exponents. So that is integral minus infinity to infinity Px. We are not writing it out fully. So here what we will have is x minus mu 2 squared divided by 2 sigma squared minus x minus mu 1 squared divided by 2 sigma squared dx. So what you can easily see now that what we have is pretty straightforward, and if we plug in the Px as our Gaussian, we are simply left with mu 2 minus mu 1 squared by 2 sigma squared, and so it is simply proportional to d prime squared. So this is going to be proportional to the d prime squared. So that shows that, okay, if the distribution is Gaussian, the d prime wasn't too far off. The d prime is actually pretty much what the assumption free method gives us. So there, that we using the KL distance, we are not going into a very different world. So it all makes sense in the sense that, okay, had it been truly Gaussian, with DKL we are getting the answer same as what we originally had by assuming Gaussian and what we were using with D prime. However, now if we extend this idea into response measures, where response is calculated in small time bins, that is, let us say now we have the response we were using so far as, let us say, this is the stimulus period, and over this entire time period we had a particular spike count divided by this capital T, we got a rate, and we use that rate in order to calculate the distributions for one responses to one stimulus and for the other stimulus. But it is definitely true that as we will see more, is that over time there may be structure in the responses, that is, the spikes do not occur completely randomly over this entire duration capital T. So, there may be some probability of occurrence of spikes in small windows, as we have discussed earlier when we discussed about the inhomogeneous Poisson process and how spike trains are. And so, what we have is, in response to stimulus 1, let us say this axis is rate in spikes per second, and this axis is time. We can bin it such that the bin size is delta, and let us say there are capital M bins starting from bin 1, where T by M equals delta. And in each of these bins there is a certain rate, that is spikes per second, and that we know we call this the peristimulus time histogram, that measures the rate as a function of time in response to stimulus. Now, to stimulus S2, this may be of some other form like this. And so, now we are asking the question that based on the overall duration of T, if we were to look at the pattern of spike over time and used all that information in discriminating S1 and S2, then how much is the discrimination, or are they discriminable? So, for that, now if we are going to use the KL distance, what I mean, there are a number of ways we can go on. So, it will depend on the size of the delta. So, depending on what delta we are using, the possible number of spikes occurring within delta is going to vary. So, if let us begin with this idea that delta is very small, about a millisecond or less, so that at most one spike can occur in one particular bin of size delta. In that case, we know that the rate becomes proportional to probability of spike in a particular window, and so we can convert the PSTH into bins where we have each bin essentially gives us some probability of spike in a particular window. This is window 1, probability of spike in this window is then again probability of spike in this window, probability of spike in this window, and so on. So, in every bin, let us say the ith bin, we have probability pi of occurrence of spike, and similarly 1 minus pi probability of occurrence of a spike is that probability of no spike. No spike in the ith bin. So, the random so we have now capital M random variables, that is the capital M different bins, and each of those can take on two values, either a spike or no spike. Let us call them 1 or 0. And now our random variable is a vector random variable, where we have that as P1, P2 up to Pm, and similarly we have another that is Q1, Q2 up to Qm, which is our stimulus S2, S1 and S2. Now, the first thing that we have to take into account is, are these probabilities independent of each other in time? So, in the case that the each of the bins are assumed to be independent of spiking in previous bins, assuming causality, there is no dependence from future bins, um, then the problem becomes easy. So, we now have to solve the KL distance between two vector random variables, and so we will be summing over all possible values of this vector p, or rather I mean um, all possible set of values of the vector p. So, this is not over sum over vector p, that would be incorrect to say. It is basically going to be the all possible 0 1 combinations that are there. So, that is essentially the 2 to the power m possible values that the vector p can take, and so this is summing over p log p by q, and so this is summing over 2 to the power m values. Let us say I equals 1 to 2 to the power m. The values of the vector p, since it is a vector random variable, and if we assume that they are independent of each other, then the joint distribution, this is by vector p we are saying this is the joint distribution of p1 p2 up to pm, and similarly this is the joint distribution of q1 q2 up to qn. So, if they are independent, we can break the p down. Let us go to the next page, that is summation p log p by q. So, p is the joint distribution of let us say probability of let us say response 1, response 2 up to Rm. Similarly, probability so let us put a suffix of S1 1 1. Similarly, response 1 suffix superscript of 2 R2 2, so Rm 2. This joint distribution can be broken down into the product of each of the distributions p1, p2, p3 up to p capital M. So, this p can be replaced by product of the pi's and log of product of the pi's, similarly product of the qi's, and this is summing over all possible values that the combination, the joint distribution can take. And so, as you can see very easily that these products can be broken down into log of sums, and when we sum over all possible values for each of these products, I mean for the entire product, the one that is within the logarithm, that particular I will contribute to the KL distance at that particular bin, and the rest of them will sum to 1. I mean rest of them will weigh the whole thing out to 1. So, that is, this is summation of this will turn out to be summation of pi log pi by qi, and summing over I equal to 1 to capital M, and so this will come out to be summing of dkl of pi and qi, and this whole sum. So, this is going from here to here is algebra that you can do. It is once you write it down and break it up, it will be easy for you to see that the ith terms will combine with the ith term. The rest of the product, because of the sum, will affected by a scaling of 1. I mean, essentially they will sum out to 1, and so it is going to be the sum of KL distances in each bin if they are independent. So, this is straightforward in the sense that when the responses are independent of each other from previous bins, then all we need to do is compute the KL distance in each bin between the white and the cyan, where these are the probability of 1 in the case of stimulus 1 and probability of 1 in the case of stimulus 2, and 1 minus that is the other value, and 1 minus the cyan 1 is the other value for Q, and summing them up, adding them up. So, basically what I am trying to say is that we write it is like this, that the response is either 0 or 1 in the ith bin is 0 or 1. It is P probability that this response probability of the response I log of probability of the response I, and this is, by the way, P ith ith bin Pi Qi Ri, where Ri goes from 0 to 1, and Pi, this I will go from 1 to capital M. So, I mean, better to put it as J. I should have this I can be actually removed. So, let us say this is probability R, and again pardon me, probability of R, this is Pi in the ith bin. The in response to stimulus 1, what is the probability that R equal to 0 or R equal to 1? These are the two things. Similarly, in the response to stimulus 2, probability in the ith bin, the response is 0 or the response is 1. So, it will be just these are the two elements that will be summed, that is, then this becomes equal to probability R equal to 0 log probability R equal to 0 or ith value Qi R equal to 0 plus Qi R equal to 0 log Pi R equal to 0 divided by Qi R equals 0. So, this is the KL distance in the ith bin, and for each of the i's going from 1 to capital M, you sum them up. That is what we showed in the next page. So, this is straightforward in the sense that it is simply a sum. However, if we now say that there is dependence, that is, when we have, let us say again, this is the stimulus, this is the entire duration capital T, we have PSTH in response to stimulus 1, which is here, and let us say we have some other response to stimulus 2, which is the PSTH. This is our rate in spikes per second, or let us say we convert it into probability of a spike by assuming that our delta is very small, that is delta times M equals T, and delta is very small, that is at most one spike. Now, Let us say in the ith bin here, the random variable r response in the ith bin takes on value 0 or takes on value 1, that we already know. But this value of 0 is now dependent on the response. So, if this is the ith bin, the actual value taken in r minus 1, ri minus 2, ri minus 3, the whatever was the value, whether it was 0 or 1, whether this was 0 or 1, whether this was 0 or 1, up to some history number of bins, let us say H bins, capital H bins. So, now the probabilities that we had in the ith bin, probability that our response is equal to 0, now has to be replaced by a conditional distribution, that is probability the response is equal to 0 given r1, r2, I mean r minus 1, r minus 2, r minus 3 is equal to all zeros, or 0 1 0, or 0, I mean all the combinations that are possible, and that will be used in the calculation of KL distance. That is, instead of just the Pi and Qi, we will now have conditional distributions Pi given the past few bins, past capital H bins, in this case let us say 3 bins, and so that will actually extend the whole process of calculation by considering the joint distribution here in the ith bin, I minus 1th bin up to I minus hth bin. So, that joint distribution is what is going to matter now, because the value in the ith bin depends on the all the previous bins. So, using that, we can now calculate the KL distance, and again we can sum this over all the i's over from 1 to capital M. So, the same idea is extended for the conditional distributions. Now, we have been talking about the delta equals such that the possible values are 0 and 1, that is, it is extremely small, and so we can replace the rate responses by probability of a spike. So, we have a stimulus over a period capital T. Again, we have bin size delta. Let us say there are m delta equals T, that is those bins, and let us say we have this is the rate, and so again we have a PSTH for the stimulus S1, and similarly for stimulus S2 again we have another PSTH. So, we cannot really use the PSTH anymore for larger delta sizes, larger sizes of delta. We have to go back to the actual spike times and then consider. So, depending on how large our delta is, let us say depending on how large our delta is, we may have 0, 1, 2, 3 or up to k spikes in that bin, just like if we were considering the whole period capital T. We had that same thing, only that we had converted this into a rate and took a whole continuous distribution. Instead, here in each bin there are k spikes possible. Now, if each bin, now we are considering larger bins, from our many repeated trials of stimulus S1 and stimulus S2, we now find out what is the probability of observing 0 spikes in bin 1 for stimulus S1 and similarly for stimulus S2. Next, what is the probability of observing 1 spike in the bin 1 and similarly for S2, and go up to what is the probability of observing K spike. So, the ith bin now takes on the response in the ith bin takes on values from 0 up to capital K, with probabilities in the ith bin Pi of 0 up to Pi of K. So, there are K plus 1 possible values. Similarly, this is for stimulus 1, for stimulus 2, in the ith bin again the possible values are 0 to K, we have Qi 0 up to Qik. So, again we can now consider first, let us say that the bins are independent. So, in each, again we will simply get the sum of the KL distances in each bin. Now, in the ith bin the KL distance is going to be similarly our response is 0 to capital K, and this is P ith bin of response log probability ith bin of response Qi of response, and we will sum over the values of response going from 0 to K, and this is going to be the KL distance in the ith bin, dKL for the ith bin. And from independence over time, we will then again sum our dKL of I going from 1 to capital M, that is there are capital M bits. Similarly, now we will not go into the writing out of it, but now if we have dependence, we again go back, instead of just Pi, we will be doing the same calculation with conditional distributions, that is Pi response equal to 0 given previous bin was 0 or 1 or K, and the even further bin back it was 0 or 1 or K, and all possible combination. It blows up very easily. So, it will require huge amounts of data for the calculation. However, this is sort of the ultimate, in the sense that this is the maximum possible discrimination, at least from an information theoretic point of view, using all the information present in the data. So, again, as we had initially said, it need not be that this is achieved by the neuron or the next neuron and so on. It only provides as sort of an upper bound of the measure of discrimination of two stimuli or a set of stimuli if we have a set of stimuli. So, with this we conclude our discussion on the all information based discrimination, the sort of the ideal observer analysis, where we are not making any assumptions about the underlying distributions or what have you. So, in the next discussions we will be talking about more biologically plausible methods of discrimination by using ideas about how the postsynaptic neuron may be behaving, and based on that we will try to understand under a set of conditions whether how much discrimination we can perform based on the responses that we are observing to set of stimuli. Thank you.